Hello everyone, I am Mahdi and I'm a postdoctoral researcher in the University of Twente. Today I'm going to present the predictive control of Achilles tendon force using an ankle exoskeleton in simulation. The contents of this presentation is also going to be presented in iCore in 3 months, sharp-ish. Somehow I didn't know anything about Fabio, and he didn't know anything about me, but we were working related research. I work in the neuromechanical lab. My supervisor is Massimo Sartori. I did optimal design of a lower limb exoskeleton and optimal control in PhD. But in my postdoc, I'm going deeper into the muscle, and I'm going to control the tendon force, which is useful for injury prevention and also injury prevention in short term, and for long term it's good for muscle fiber remodeling. Our approach is to keep the tendon force under a certain threshold. Our controller should be fast to do this, and we want it to act as an assisted knee strategy. This is the exoskeleton, the ankle exoskeleton that we're going to apply our control algorithm. We call it JLO. And because of these specifications that we want, we're going to use monoperative control for control. The thing about monoperative control is that, as you all know, it needs a good and fast model. And a problem with the current model in the heel-tied muscle model is that, for example, this well-known heel-tied muscle model has a closed-form solution, but the problem is when the activation goes near zero, it shows some unstable behavior. We can resolve this behavior by adding a damping to the model, but the problem is now that there's no closed-form solution for this model. There are some research done by Van Vogers and fellow Klute, which use implicit methods, and also Matt Miller uses numerical methods, but we're interested in finding a closed-form solution. We're going to use the force-length relationship is straightforward and it's not challenging when modeling, but as Fabio said, the main problem and the main challenging part is the force-velocity relationship. There's a paper that Matt Miller had. He stated that the absolute value of the normalized velocity of a muscle in different types of walking and running is always less than 0.5. So we're talking about this region. As you can see, in this region, the force-velocity relation is almost linear, so we can use this to solve the obtain the tendon force in a closed form. The model gets so much simpler, and we're going to verify our model using the Cinemas toolbox that we have for obtaining the tendon force online. You can see that the performance of the model is acceptable for our application. It's the Solius and Lapias. You can see the graphs here for the nanometer and for Solius in different speeds, like about 1 kilometer per hour and 8.5 kilometer per hour. So running, it has a good performance, you can see, for this model. And another good feature of this model is that, for example, Cinemas estimates that tendon force in 0.5 milliseconds, so online, but our model, because it's closed form, it does it in 6 microseconds. So it's pretty good for predicting the future. So wrapping up, we're going to control the tendon force using JLO. This is the system. And we can, for hopping, we can simplify the model with this mass and body system. I can show you it after the presentation if you want. And we can obtain the governing equations in state space form. So because we have a closed form equation for the tendon force, and we can write the equations of motion of that mass, we can have the system's equation in state space form, which is very good for model-based control. So this is the structure of the controller. We have a predictor that predicts whether or not we're going to exceed the limit of the tendon force in the future. If no, the MPC wouldn't be active. If yes, it would get enabled and control the actuator. These are the simulation results. We're applying different activations in the muscle. And in this figure, you can see the red one is without assistance and the blue one is with assistance. You can see that activation is changing. So from 0.8 it gets to 0.9 and gets to 1 in the future. And the controller performs well in these situations. Also in different frequencies of activation, it also performs well. In the future, first of all, we're going to implement it on JLO. After it's constructed, it will take like 1 or 2 months. And we're going to also apply it on a trunk exo. Another future work with which we're now working on is predicting desired muscle tendon force using primitive muscle synergies and muscle reflexes. Yeah. Thank you.
Would the trunk exoskeleton then be controlled by one like back muscle, or would you imagine many different muscles?
We haven't like started yet, but I think it's going to be with one big muscle.
How do you adjust your muscle model to subject specific origins?
We're relying on the model that Cinemus is using. Cinemus is using the similar muscle model with damping. That's like we're going to use the parameters used by Cinemus.
So the same parameter for everyone.
Yeah.
Not
No, the Cinemus adjusts. You have to like do calibration, and that goes.
By primitive muscle synergies, do you mean the activation patterns of muscles? So, and by muscle reflexes, how do you think of implementing that?
Well, we're thinking of how to adding the delay in the equation. So that's a bit, we're struggling with that. But yeah, it's the future work we're going to do that. Yeah.
Presumably the big picture is you protect an Achilles from being hurt when there's an exceptional action where you would normally bring an Achilles, it's a weird exceptional action. That's the premise, is it not?
Yeah.
Presumably you're then worried that all your muscle models are based on unexceptional actions. Do you have a shocking list of experiments that you want the physiologists to perform to go, here are the weird ones to populate your muscle models with?
I'm not sure if I understood it.
So if I had a mouse with a hammer, but make that a sensible question. We're asking a muscle model that isn't built for this job to extend to the weird condition where you snap a tendon, which is really not what we normally do. Were there to be an ethical animal model where we could chase down the bits of the muscle model that is very important for you, but not for normal walking? Can you imagine a mouse experiment that you should be performing?
If the specification of the, for example, the force velocity relation is going to change, then yeah, this model doesn't work on that. But if not, so same graphs, almost same graphs, so use this linearization technique to like, account for that.
I guess, can I add a little bit to that? So what I would think about more with this is when we're talking about something where you're protecting the Achilles from damage or from a dangerous situation, it's no longer in the linear region of its force deformation curve. It's going to be up in like a plastic region that most of our models are not expecting to work in. So the muscle itself is working on the same force velocity curve, but the tendon that's attached to it and is of importance is no longer working with the parameters that we have plugged into the model. If there are in vivo or ex vivo testing methods with cadaver specimens or animal models or whatever else, are there things that we need to start, kind of banking down if we want to build out these models in the future?
So if we know that, for example, what the muscle velocity is, what the region of the muscle velocity is, we can linearize in that region. So the thing is, we have to have a linearized force velocity relation to be able to use this. So we can linearize around that region that is important for us, and we know that it's like crucial, it's dangerous for the muscle. So when we're in that state, then we have to use, switch to another model. So another model of having a linearized FV relation, force velocities.
One more question, maybe?
Yeah, I don't know whether it's a true question, but when I heard you present, I thought you wanted to reduce the loading in the Achilles tendon.
Reduce the what?
Reduce the loading in the Achilles tendon in a scenario where there had been an injury and the tendon had to recover. But then the questions you got were about preventing the Achilles tendon, a snap of the Achilles tendon. And I was just wondering, could you clarify which of the two scenarios you're looking at?
Well, I'm going to prevent the Achilles tendon to reach a threshold, for example. I can also, using NPC, because it's an explicit model, I have, I can also limit the velocity of the muscle. So I can limit the velocity to reach that threshold, and another threshold that we define. So it's just constraint, and we can handle it with NPC. So we can derive the control input somehow that we don't reach the dangerous part of the force velocity range.
Thank you very much.